Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I have a course on machine learning. And today we're going to get into support vector machines, a very fascinating methodology that's going to allow us to explore some ideas around projection into higher dimensional spaces in order to solve for more complicated models. All right, so let's go ahead and get into it. What's our motivation? Why do we want to cover this technique specifically? Well, it's a very powerful form of machine learning for prediction, supervised learning. The method is used for the purpose of segmentation, for the purpose of coming up with a boundary by which we can separate into two classes. And so specifically, we might have a spatial boundary as shown here, and we might want to come up with some methodology where we can separate a boundary whereby we can separate between the two classes, the red and the yellow cases. Now we could also be dealing with a multivariate boundary, which is pretty typical classification problem, where we have the predictor features 1 and 2 up to some high dimensionality perhaps, and we want to formulate some type of boundary by which we can predict the yellow and red cases. Okay, so that's what we want to be able to do. Just some general comments about the approach of support vector machines. It's a generalization of the linear decision boundary for classification. We can apply it for classification, optimal segmentation, using boundary hyperplanes, specifically in cases where the categories overlap with each other, where we don't have a nice clean segmentation. That's exactly what support vector machines was designed to do very well with. It imposes nonlinearity in that decision boundary by transforming to a higher dimensional feature space. And I'll show you how we do that with what we'll call the kernel transform. And it maximizes the separation between training data of different categories, and will introduce the concept of margin in order to do that. Training data well within the decision boundary will have no influence, and that gets us into the idea of training data being assigned as support vectors or not. And so let's get into it and talk about this methodology. We're going to go through 4 separate concepts related to support vector machines with a little bit of illustration to try to explain it. We want to form a boundary that has the largest possible separation between the different cases, the yellow and the red cases. This is the example again where we got 2 predictor features. Where course could work with many different features. This could be high dimensional, but we'll just show it very simply with 2 predictor features. We want to form a decision boundary such that we do the best job possible separating the yellow and the red cases. Now, they don't have to be separable, but we want to do the best job we can separating them apart from each other. And so we'll introduce the concept, and we'll define it more rigorously later, that we have a boundary, and around the boundary we're going to have some margin. And that margin is going to be important. It's going to help us determine where to put the boundary. And our idea is that we want to get the data on the right side of the margin. In other words, we're not comfortable if the data are on the right side of the boundary. We want, in fact, them to be outside of the margin. That's really the goal. Okay, so now we have a margin. The dashed line indicates a margin around our boundary. Now, what we're going to do now is any data that lies within that margin or on the wrong side of the decision boundary, we're going to call those support vectors. And so we look at our boundary right here, our nonlinear boundary, we got our margin, and any data, this is the red side, this is the yellow side, any data red or yellow within the margin are going to be support vectors, and data that are on the wrong side, the yellow data, training data on the red side, the red training data on the yellow side, they're outside the margin, but they're on the wrong side. And so they're going to be called support vectors. So what we're going to do is we're going to do an optimization to try to maximize the margin, minimize the regularized error jointly, and I'll show later on exactly how we're going to do that. The regularization, we'll put some weighting or cost on it, cost constant. And we're going to do this such that the training data well within the correct region, all of this data here, all of this data here, are going to have no impact on the model. And so that's really interesting, because imagine in this setting here, I could have 1 million training data that are correctly classified in the red region. Do I want that to update the boundary? Do I want the boundary to move further away, come closer? How should that impact the boundary? Well, if it's already correctly classified and it's not in the margin, therefore it's not close to being wrong, we don't want it necessarily to update or change our model. That makes a lot of sense. We could have 1 million red values right here, and it may not make sense for that to have an impact on the boundary. The boundary's working. That's a very interesting idea. Now, what we're going to do is we're going to project the problem into a higher dimensional space to impose nonlinearity. We'll do this using a variety of different kernels. In fact, spoiler alert, that's why this is called support vector machines, is because you can change the kernel and get a different machine for your classification. So whereas in the original space we have this nonlinear boundary, we project it to a higher dimensional space, and in that space our boundary is going to be linear. Beautiful. Now all of the math is easy. All of the calculations are easy. We know that we're going to have a simple optimization. And so that's what we're going to do. We're going to project to a higher dimensional space in which we can model with a linear, like a hyperplane that's going to divide up the data set. So we got a simple model in that space. All right, point number 4. We're going to have a C parameter. It's a cost penalty of misclassification. High C will result in a more complicated model. Lower model bias, but we trade off. We get a higher model variance. And so C is going to be our regularization term. Remember ridge regression? That whole idea of having that regularization? Same type of thing. It's going to be our nice hyperparameter that we can include to control the degree of fit. High C, I'll show later, will drive you to a smaller margin. Less support vectors are going to be included. Something like this. And then as a result, you'll have a tendency to overfit. A small c, larger margin, now you have more support vectors, and you'll tend to be driven towards underfit. So that's really nice. We got a tuning hyperparameter that we can work with. Okay, so let's talk about what the model looks like. So it's not too bad. In fact, all we're going to have to do in this high dimensional space is solve for this hyperplane right here. And if we show this in vector math with that, so the x and betas are going to be vectors, and so we'd expect that we're going to solve for coefficients over the 1 through m and different predictor features that we want to work with for our model. Now, what's interesting is that if you look at this function, that you'll find that it's proportional to the signed distance from the boundary. It's going to be negative on one side, positive on the other side, and the result will be 0 at the boundary. And the proof is available in Hasty and all. I'm not going to go through the vector math and the proof for it. So what that tells us is that the sign of that function for any possible combination predictor features is going to tell us the classification. Positive for, say, red, or negative for yellow, depending on how we have the data there. So g of x is just going to be the sign. That's our prediction model. And so this is pretty good. So we can represent a constraint of all data of each category. The training data must be on the correct side with this simple equation right here. Because the result coming out of this plane will be negative or positive. And if we're saying that we expect that for positive training data, if we assign positive as a value to, like say positive 1 to all values that are red, and the equation comes back and says, yep, positive, you're on the right side, that would be greater than 0. And if negative for the yellow cases, and the actual model comes back and says, yep, negative times a negative is positive. And so we would expect that this would be our constraint, that this product must be always greater than 0, would say we always correctly classify all of our training data cases. Okay, so that's really good. That's what we're looking for, and that's a good model then. So now talk about the concept of the margin. And so what's going on here is when training data are categories that are overlapping with each other in the predictor feature space, it's not really possible to satisfy this equation. It wouldn't be desirable. We'd be completely overfit to try to get a model for which that case is always true. So we don't want to have a model that's going to be overfit. Let's develop a decision boundary that will be able to allow for some misclassification. And this will be very, very practical for us. This will be very helpful for us. So let's go ahead. This model is now updated to look like this, where M is this distance right here from the boundary to the margin. That's going to be, and 2 times M is going to be the width of the margin, the total width of it, and it'll be centered on the decision boundary. Now what we can do is we can introduce the concept of error relative to the margin. Now remember, I said before, we don't want any of our training examples to actually be in the margin. And so we'll consider that to be error. So this is the clear or no fill data locations. This is the gray fill data locations on this side of the boundary. And so everything's an error if it's in the margin or on the wrong side. And so you see this hollow or no fill data, training data right there, it's going to be considered to have error, and that error is going to be equal to the distance from the margin right there. So basically this is going to be considered error. Now of course this is a case right here where the no fill case is on the wrong side of the boundary, and so the error is going to be right here. And then we have other cases right here where we have data that are on the right side of the boundary, not in the margin. They have no error. And this one right here is way on the wrong side, even outside of the margin, but on the wrong side. So its error is going to be this entire length right here. And so we can summarize the error over all of our training data relative to this concept of margin, but also acknowledging that all of the data correctly classified outside of the margin have no error. Okay, so they won't contribute to the error at all. And so what we're going to try to optimize for, we're going to go ahead and solve this quadratic with linear inequality constraint. And it's really good because it's going to be a convex optimization problem. So we're not going to have, it's going to have a nice global minimum. We're not going to have a bunch of local minimum issues. And so we can take it and re-express it as simply finding the parameters of that high dimensional. Remember, we're projecting into a higher dimension, hyperplane. Its parameters, the beta and beta naught and so forth, and whatever dimensionality that space is in, we're going to set those parameters such that we minimize this following terms right here. So the summation will include the margin, the size of the margin. Now notice that's in the denominator. So we're going to be maximizing the margin. And the C regularization term, the cost penalty of error, times the summation of those errors. And I showed a whole bunch of cases of those error terms of all the values, training data values that are in the margin or on the wrong side of the decision boundary. So we're going to go ahead and simultaneously maximize the margin while minimizing the error at the same time in that high dimensional space. That's what we're going to do with our model. And so let's just make a couple of around this. Now, first of all, we've already said it. We're going to maximize the margin while minimizing the error, and we'll find the very best boundary to do that. Now, if you look at the terms right here, we have that C hyperparameter, our regularization term. It's a cost of error. And so higher C will result in a reduced margin. It will make error more important than trying to maximize the margin. And if we reduce the margin, the size of the margin around the boundary, that will lead to overfit. Smaller margin, fewer data are used to constrain the boundary, and you get more of a detailed boundary. Now, the other thing too, and this is a good reminder, if we look at all of these terms and everything going on in the equation that we're minimizing, we're picking the very best hyperplane to minimize this, it reminds us once again that training data well on the correct side, outside the margin, on the correct side of the boundary, will have no influence on the result. All right, so now let's go back and do a little bit of a recall and think about this whole issue around projecting to the higher dimensional space, a basis expansion. And so we covered this back during polynomial regression. And we mentioned the fact that we can do a basis expansion to add flexibility to our model. We capture nonlinearity in the model, and we could apply it in regression and classification. It was really cool because we gained flexibility, but we also still had the ease of solving the problem. And so we got all into that before. So basis expansion, just a reminder, in the case of polynomial expansion, we have a predictor feature xi. We could do a second order expansion to x squared, third order, x cubed, and so forth up to the kth order. And the result is if we did that across all of our predictor features, whereas originally we had a data table, predictor feature data table of n samples and m predictor features, now we'll have n samples and m times k, the kth order we go to, predictor features. And so we're in a higher dimensional space. This is great because we can now integrate nonlinearity. We can actually build a more complicated decision boundary. Now I took these images from this blog right here. Want to give credit right here. Here's the citation or location I took it from. And let's just think about mapping to higher dimensional space in order to get to a point where the training data can be separated by some type of linear model. If we take m equals 1, we have one predictor feature, and this was our cases. These were our cases of training data with red and blue values. Clearly, that cannot be separated by any type of a linear model. We just wouldn't be able to separate it. And now if we project it to a second order polynomial, and so now we have predictor feature x squared and predictor feature x, you could now fit a linear decision boundary, this vector right here, through it, and we could actually separate this data set, the blue and the red. So that's really cool. Now we could extend it from 2D to 3D by projecting to a higher dimensional space. And so this is an example right here where we have the blue data are all around the red data, and we could never separate that. We could not come up with a plane, or in this case in 2D, a line that would be able to separate this setting. Now, if we were to apply an expansion to a higher dimensional space, in which case the space has been kind of rounded like a bowl, what would happen is these blue values right here would be higher up and the red values would be lower down. And if we look at it from this orthonormal type view right here, you would see that we could in fact put a plane through it, and that would be a linear decision boundary that could now separate that data. So this is the whole idea of support vector machines. Get to a space where you can now separate with a linear decision boundary. Now, a student in my class asked, can we guarantee that the data, training data, is separatable in that higher dimensional space? And the point is we can't. We can't. We have to decide on where to project it, and then we do our best in order to fit the best plane, maximizing the margin, minimizing the error with our regularization term, and we get the result back. Now, we're not saying that we're guaranteeing it's separatable, but we have to make a good decision of where to project it to get it to be separated. Okay, now let's talk about the kernel trick. Now, this is really cool. In summary, what we're going to say is that we will project into a higher dimensional space, but with the kernel trick, we can solve for the model, we can solve everything without ever actually calculating the values in that high dimensional space. All we need is a measure of the degree of similarity between the training data in that high dimensional space, and then we can solve the whole problem. We can solve the boundary, and for many cases, many projections, we can easily calculate that degree of similarity between the data. Okay, so let's talk about this in a little more detail. Okay, so if we look at the math associated with calculating our decision boundary, what you'll find is you're only going to need the inner products over the predictor features projected in this dimensional space. And if these inner products are really just a measure of the degree of similarity between all of the training data examples. And so instead of actually having to transform this h of x, which is the transform in the higher dimensional space of your original predictor feature x, we don't ever have to calculate that. We just need these inner products, which is going to be a matrix, a similarity matrix between all of the training data projected into that higher dimensional space. We never actually need the training data values in the high dimensional space. Kind of funny, eh? We actually never go to the high dimensional space in order to solve this problem, in other words. Now, what's fascinating are there are examples of kernels that do some really crazy things like project to infinite spaces and so forth. Because we never have to go there, we don't actually have to calculate the values there. We just need to know the degree of similarity there. Anyway, I like to throw in some mind-blowing things. I don't know about you, but I'm still kept up at night thinking about the idea that in high dimensional spaces, it all becomes corners. And when we're talking about the curse of dimensionality, it's fun to think about these things. But practically speaking, let's just bring it back home. All we have to do is calculate this kernel matrix, which is going to be a measure of similarity between all the training data. Now, is that because it is this similarity matrix, and it exists within this high dimensional space, it should be consistent. And so one of the things that we would expect is it's symmetric. The degree of similarity between training data 1 and 2 is the same as the degree of similarity between training data 2 and 1. And we would also expect it to be positive semi-definite. Now, as I mentioned before, we don't need to go to the high dimensional space. We just need to formulate this kernel matrix, this measure of similarity, in order to work with our kernels. And so here's some examples right here. The linear kernel and the radial basis function kernel that are shown right here. And what you'll notice is that we can take our training data and across our features, we can go ahead and calculate this degree of similarity right here. Just simply the values over the features transposed and applied to the other training data value, all its values over its feature. And the radial basis function is shown right here. Not a big deal, because what you'll see is that this right here is just the square Euclidean distance between the feature vectors. And so we would expect that as they're more similar to each other, that this degree of similarity would be larger because of the negative of the exponential right there. And so all we have to do is calculate these similarity matrices, the kernel matrices. We never actually have to calculate any h of x's, which is really, really cool. Okay, so once again, we call this methodology support vector machines because all we have to do is plug and play a new kernel and we get a totally brand new machine to work with. Okay, so what we'll do in the next video is we'll go through an example of support vector machines. We'll show it for a classification problem using petrophysical geophysical information. I hope this lecture was useful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and conduct research in data analytics, machine learning, and geostatistics with a focus on spatial problems. If you're ever interested in hearing more, well, I put all my lectures on YouTube. And so you're watching this one right now. You're probably on my YouTube channel. And I have all the examples shown or demonstrated in these lectures available on GitHub. Geostats Guy is my account there. You can check out all my repositories. And if you have any questions, just go ahead and shoot me an email. Let me know if you have any suggestions or feedback or anything from these lectures. I love to hear from people. All right. Hey, take care.